let's go on to techniques of integration. So this chapter is definitely very important for calculus 2. How do you find antiderivatives, indefinite integrals? Okay, techniques of integration. Basically, how do you find indefinite integrals? Right, that's important. For derivatives, it's kind of nice because basically for every function that you have, if I ask you to find its derivative, there's just a nice set rule that kind of tells you what to do, right? You've got the power rule for power functions, you got the product rule, quotient rule, chain rule, right? All those nice rules for finding, and then there's like implicit differentiation, etc. But basically, I could give you any function theoretically at this point, and you should be able to find its derivative, okay, using one of those set rules. For integrals, for indefinite integrals or antiderivatives, the story changes a lot. There's no real set rule that you look at an integral and say, oh yeah, that's the rule I have to use. Although some of them, yeah, you could probably say that. But for a lot of integrals, it's like it takes a lot of experience to figure out maybe what technique you could even try, and those techniques may not even work. In fact, some integrals, and a lot of them, in fact, most of them are just not doable by elementary methods, by these methods that we're going to look at here. However, it's really important that we at least see what these methods are so that we can know how to do the ones that we can do. Okay, and so the first formula that we're going to look at is called the formula for integration by parts. And then the next one after this, we're going to do, what is the next one? Integration by trigonometric substitution. That one is a real bear. And then finally, integration by partial fractions. So those are really the three major methods that we're going to learn this semester. And that really covers pretty much everything. But unless you want to go on to like, advanced calculus and stuff like that, really this is what we have. There's a few other techniques like integration by series. In fact, we will see that at the end of the semester. But for now, these are the important ones for us. Integration by parts. So what is this? So just let's recall, I'm going to try to show you where this comes from. Recall the product rule. What does the product rule say? It says if I want to take the derivative of a product of two functions, everybody remembers the product rule? That says we take the first function times the derivative of the second, or whichever order you want to say it. I guess the derivative of the first times the second plus the second function times the derivative of the first. In fact, let me write this a little bit differently. I'm going to do it like this instead. I'm going to say f of x, g prime of x, plus g of x, f prime of x. Right. So that's the product rule. So what I want to do here is integrate both sides of this. Okay, I'm going to integrate both sides of this equality here. So I'm going to integrate this. Okay, now next I want to move that. I'm going to rearrange things a little bit here. I'm going to leave this f of x, g prime of x by itself on one side, but so I'm going to move it over here, in fact. And then the other stuff is going to go to the other side of the equal sign. So really all I've done is just written down the product rule, and then I just integrated both sides of the product rule, and then I just rearranged things a little bit here. So notice that what happens in particular right here, when you take the integral of a derivative, what happens to that? Aren't the integral and the derivative just sort of kind of inverse operations of each other? And so when you integrate a derivative, don't they just tend to cancel each other out? Basically what we get is this. Yeah, we get the original function back. So basically that just means in this case, we're just going to get f of x, g of x. And then this stuff stays the same. Okay, now this is actually the integration by parts formula, but we typically write this in a little bit of a different way. If we say, let's let u equal f of x, then du dx, or well, really we can do it like this. We could say du is equal to f prime of x dx. If you want to see actually, let's just go ahead and write the entire thing here. Really, what we're doing here is kind of using the idea of a differential. If I differentiate both sides of this, I get du dx is equal to f prime of x, right? The derivative is just f prime. And then if I multiply both sides by that dx, this gives us that differential formula back from calculus 1, if you remember that. We get that. And then if we let v be equal to g of x, then we get similarly dv is going to be equal to g prime of x dx. And so if we do that, what we'll see is that this formula here becomes what? Integral f of x we said was u, and then g prime of x dx, see what that is? That's dv, right? G prime of x dx, g prime of x dx, that's dv, right? So that becomes u dv is equal to f of x g of x, that's u v, minus the integral, and g of x we said was v, and then f prime of x dx, right here's where I am, f prime of x dx, we said that that was du, right? So this then becomes v du. So that is the integration by parts formula right here. So basically what we can do with this formula is we can basically identify the two parts of an integral that we're trying to find and then rewrite it in this way, uv minus integral v du. Okay, so let's see an example of this technique in action. So let's look at, do we have any questions over this formula first of all, before we can continue? Seems not, so let's clear this out of here. So typically the integration by parts formula works best when you have two different types of functions being multiplied together as your integral. Okay, different types meaning like you have, what types of functions do you have? You have algebraic functions, right? That's like x squared, square root of x, anything like that. Then you have the so-called transcendental functions. That's like sine and cosine and all the trig functions. And then you have the exponential functions and logarithmic functions and inverse trig functions, all that stuff. So basically, anytime you have a couple of different types of functions multiplied together in your integral, this is where you're going to want to be at least trying to do integration by parts. So here's a good example of that, because what kind of functions do we have here? Well, x is an algebraic function and cosine x is a trig function. So there's two different types of functions. They're multiplied together. So this is a perfect one for integration by parts. Again, anything that I'm really saying about these rules for integration, they the thing about integrals is that it's not really a rule. It's more of a suggestion. And often, well, not often, but a few times you'll come across situations where, oh, it looks like that needs to be done by parts, but in fact it doesn't. So in general is what, when I say like, you know, when we see two functions of different types multiplied together, in general, we'll try integration by parts, but not always. For the most part, yes, but not always. So what do we want to do for integration by parts? We just want to identify the parts. And so since, if you see on the left side of the formula, it says u dv, right? U and dv. So that is the two things that we need to identify right away. What what makes up the u part of this integral? What makes up the dv part of it? Now, to help you determine that, which one is should be which, we have this nice little memory aid here. I don't know if you guys have heard this before, but liate. That's a memory aid that you can use to try to decide what u should be. Okay, this is for u, not dv. This is for u. What does this stand for? Well, what does the L and the I and the A and the T? L, logarithmic functions. That's the first thing on the list. That is, if you have any logarithmic functions in your integral and your integrand, that would be what you'd want to make u be. Okay? I, inverse trig functions. If you have any inverse trig function, if you don't have any logarithmic functions, but you do have an inverse trig function, then that would be your choice. A, algebraic functions. Okay. And then T, just regular trig functions, not inverse trig functions, regular trig. And finally, E, exponential functions. Okay. So there's your memory aid to help you to decide what you should make U be. So based on that, what should we make U be in this particular integral that we're trying to do? X or cosine X? Well, let's see, according to our Liate, we don't have any logarithmic functions. We don't have any inverse trig functions. We do have an algebraic function, though. X is an algebraic function, so that's what we have to make U be. That means that the rest of the integral has to be dv. Well, what's left? Cosine x dx. The dx is part of the dv. Cosine x dx. Yeah, no problem at first. It's hard. This is the first time we're saying it, right? So don't feel bad if you make a mistake right away. Um, Once you've figured out what u and dv are, then you also have to figure out what du and v are, because those are also part of the integration by parts formula. So du is simply the derivative of u, so that's just dx. V is the antiderivative, because this is dv, right? So that's like the derivative already, and we have to find the antiderivative. So basically, this is how you find v. You have to integrate dv. And what is that? In this case, that should be just sine x. So v is sine x. Okay, now that we have identified all of these things, we put them into the parts formula then. Okay, so that means that integral x cosine x plugged into the parts formula. What does the parts formula say? uv is first, right? uv. So what's u and what's v? Well, u is x, v is sine x, so x sine x, minus the integral of v du. Well, so v was sine x, and du is simply dx. So you can see why this is a good thing to do, right? Because what do we have left now? Now we have an integral that's pretty easy to do, right? The integral of sine x by itself. We've got x sine x. The integral of sine x is going to be negative cosine x, so that becomes plus. And then we just put the plus c on the end, and there we go. There is our antiderivative for x cosine x. Okay, any questions on that? Yeah, in general, I guess just to say a little bit about the sort of overall structure of the course here, we have started out by doing a bunch of application stuff, right? Like what are the applications of the antiderivative, or applications of the definite integral, actually. And now we're moving on to techniques, right? And that's going to take up about maybe a third of the semester, man, not even quite a third of the semester. And then we'll do some more applications, and then at the end of the semester, we do the dreaded sequences and series, which are actually really cool. So I hope the dread maybe will go away once we start seeing them. All right, so there's one example of integration by parts. Any questions on that one? If not, we'll go ahead and do the next one. All right, so now we have a definite integral, which is fine. The fact that we have a definite integral, of course, we're going to get those occasionally. So x ln x. Okay, so again, this starts out exactly the same way, whether it's definite or indefinite. Identify u and identify dv. In this case, again, with Liate, right away, L, logarithmic, so right there, u should be ln x. That leaves that dv should be the rest of it, x and the dx. Then du, remember, is just the derivative of u. That's just going to be 1 over x dx. And then v is the antiderivative of x dx, which is going to be 1/2 x squared. So yeah, don't forget that when you have dv, you have to find v by an integral. Okay, so you can kind of see that integration by parts actually requires you to do two different integrals. The first one is to try to find v. The second integral is the one that you get when you plug it into the parts formula and you have uv minus integral v du. So really you have to do two integrals by an integration by parts. Okay, so according to the parts formula here, I'm just going to do the indefinite integral right now, and then we'll come back and do the definite part of it at the very end. The indefinite integral for x, ln x, according to the parts formula, uv, so 1 half x squared ln x. That is the u times the v, minus the integral of v du. V du, we've got a 1 half in there, we'll put that out front. And then we've got an x squared, and then we've got a 1 over x, right? So x squared times 1 over x is just x. See that? That's the integral v du. Make sense? Then we actually have to do that integral, so we're going to get 1 half x squared ln x. Antiderivative of x is just 1 half x squared, so we're going to get 1/4 x squared. So there is our antiderivative of x ln x. Any questions about how we got that? We still have to do the definite integral part. So then that means that if you have questions, just go ahead and write them in there. I'll stop. The definite integral now that we have an antiderivative, we can use the fundamental theorem to do this. Right now we have our antiderivative, 1 half x squared ln x minus 1/4 x squared. Plug in the two bounds. We get 1 half 2 squared, that's just 4, so let's just write that 1 half, yeah, 4 ln 2 minus, if I plug in 2 there, I just get 1. When I plug in 1, I'm going to get ln 1, which is just 0. When I plug in 1 on the other one, I'm going to get negative 1/4, but I'm subtracting it, so I have to remember that becomes plus 1/4. And so our final numerical answer here would be 2 ln 2. Let's see, minus 1 plus 1/4, that's minus 3/4, I guess. 2 ln 2 minus 3/4. Okay, any questions about that one? Number 2, integral of arctan x. Now some of these, like I said before, they're not really rules, they're just suggestions. And this is one of them where you look at it and you say, well, this isn't the product of really anything. It's just a single function that we're trying to find the antiderivative for. So there's no product here at all. Well, that means there's really no choice about what you want to make u be. You have to make u be the integrand itself, arctan x. And then dv, that only leaves the dv. So there's a few like this where it's just a single function, but you still have to do it by parts. And if it's a single function, not multiplied by anything else, and you're trying to do it by parts, well, that you don't have to bother with that liate at all because u has to be the function itself, and then dv has to be just the dx. That will always be the way it is if there's just a single function and you're going to do it by parts. So if that's true, then now we have to find du. So let's try to remember, what is the derivative of arctan x? Again, this is something that, you learned it in Calculus 1, so we need to remember it. What's the derivative of arctan x? You remember that? 1 over, yeah, x squared plus 1, right? Or 1 plus x squared, exactly. 1 over 1 plus x squared, and then the dx on the end. dv is dx, meaning that v has to be x. The antiderivative of just dx, which is 1 dx, is just x then. Okay, so that means then that this is equal to u times v, right? uv is x arctan x minus the integral of v du. V du is going to be x over 1 plus x squared. See that? Everybody okay with the parts formula so far? So take a look at that integral that we're left with here, right? X over 1 plus x squared. When you're doing integration by parts, you want this integral to be something that you can do, right? Like it has to be able to be done by some sort of other elementary method. X over 1 plus x squared, if you remember, that's not that bad, actually. How do we do that integral? How do we do this one? The method for that one. Well, since there's if you look at the denominator and you think about its derivative, well, the derivative of the denominator is it shows up in the numerator, right? So that's like a big hint that this should be done by substitution. So we'll do this by u substitution. So this actually happens a few times in integration by parts, where it's an integral that you actually end up with itself has to be done by some other method. And so u sub is the case here. So we'll make u be 1 plus x squared, and we'll make du 2x dx. And then if we notice up here on the top, we've got an x dx, right? Not a 2x dx. So we can get rid of that 2 by dividing. We get 1 half du is equal to x dx. And so our new integral here will then be uv, or I'm sorry, this is integration by substitution. So this one then just by itself becomes 1 half integral du over u, right? Du over u. And remember that one, the integral of du over u is just natural log of u. Okay, everybody good with that? And so that means then our final answer here is just going to be it's equal to x arctan x minus 1 half natural log of 1 plus x squared. Any questions on that one? So the antiderivative of the arctangent function is all of that. That means if we were to take the derivative of all of that stuff, x arctan x minus 1 half ln x 1 plus x squared, if we take the derivative of that and simplify it, we should just get arctan x out of that. Okay. All right, so there's no questions there. Let's try a couple more, just to kind of see like everything that we can maybe expect to run into when we do integration by parts. There's a few things we have to be kind of aware of here. For example, what do we do when we have something like this? So again, we have two different types of functions multiplied together. We got an algebraic function multiplied by an exponential function. And according to Liate, L is first, there's no logarithmic, no inverse trig. The third thing is algebraic. We do have one of those, x squared. And then dv then must be e to the x. Remember, the very last letter on that is e, right? So the last thing we would ever want to make u be is an exponential function. Then we find du is 2x dx, and then we find that v, the antiderivative of e to the x, is itself e to the x. And so putting those into the parts formula, we get uv, so x squared e to the x, minus the integral v du. There's a 2 on that, and then we get an x e to the x. Okay, so there we are. That's what we get. Now we look at that new integral that we have there. We'll have how do we do that new integral? X e to the x. Well, that is also a product of two different types of functions, right? And so that tells us, well, there's really only one method that we have at our disposal here, and that's integration by parts again. So we have to do it again. So for x e to the x, let's do parts again. U is equal to x. Du is now just dx. dv is equal to e to the x again. And then v, again, is the antiderivative of that, just e to the x. And so we'll copy the stuff we already had, x squared e to the x, minus 2, and now we have an integral there, right? X e to the x. That, we're doing parts on that. So uv, so now we've got x e to the x minus the integral v du. Well, in this case, v is e to the x, and du is just dx. So that's what we're left with now. But now we can do that last integral, right? It's just itself. The integral of e to the x is just e to the x. So let's finish this off and distribute that 2. And then it's actually a minus 2, so it'll become a plus 2 on the end of this. And then just integral of e to the x is just e to the x. And so there we go. So there's our antiderivative of x squared, e to the x. So I guess the point of this example is just to show you that occasionally you will have an integral where you have to do integration by parts more than one time in the same integral. Okay. So let's try b. Okay, so now in this case, doing Liate, t is before e, so we're going to make u be sine of x. That leaves that dv is e to the x. It turns out that this is one of the only integrals by parts where you can actually make u be e to the x. In fact, we could switch these and it wouldn't change anything. It would still work. But let's just go with Liate anyway. So du then, derivative of sine is cosine. The antiderivative of e to the x is just itself. And putting this into the parts formula, we're going to get this is equal to uv, so e to the x sine x minus the integral v du. Integral v du, so that's e to the x cosine x. Okay, so now if we look at that new integral that we have, e to the x cosine x, well, that doesn't look any easier than the one we started with. It just looks like e to the x sine x, except it's a cosine instead of a sine. So that, I'm not sure, does this help? Are we kind of stuck? Well, maybe, but let's see what happens if we just say, well, since we already tried integration by parts once, let's try it again on that new integral. So we're going to say u is equal to, again, we'll say this time cosine x, and then dv is e to the x. And then du will be negative sine x, and then v will be e to the x. Okay, so then we'll see what happens when we do that. Then this integral here is going to become e to the x sine x, stays there, minus, now we have a new set of terms to do here, right? uv, that's going to be negative, oh, I'm sorry, e to the x cosine x, right? E to the x cosine x, minus the integral v du. But du is already negative, so that's actually going to become plus the integral v du, so e to the x sine x. Okay, so is this helpful? Are we to a point where we can actually do something with this? Well, if you look at what we've got here, I'm going to go ahead and just rewrite everything we've got up to this point. We've got this e to the x sine x integral. We did the parts formula 2 times, and this is what we ended up with. E to the x sine x minus e to the x cosine x minus the integral of e to the x sine x. And that's where we are after doing the parts formula 2 times. What do we notice is going on here? Look at that new integral that we got. Well, it's exactly the same as the integral that we started with, right? E to the x sine x. So we can actually just treat that integral as if it were a variable, and we can just add it to both sides. So we can just say, let's add that integral to both sides. And I'll add it over here too. Well, since I have exactly the same thing on the left side, when I add one integral of something to the exact same integral of that something, that means there's just two of those integrals. So I'm just going to get 2 integral e to the x sine x. And then this one we can maybe factor out an e to the x, save a little bit of writing. And now look what we've got here. 2 times the integral of e to the x sine x is equal to this stuff on the right side. Well, that means that if we want to know what this integral is, we can just divide everything by 2. And then on the right side, we just have an algebraic expression for that antiderivative, right? So 1/2 e to the x times sine x minus cosine x. And then we could put our plus c on the end, and there it is. So there's our antiderivative. Kind of interesting how that works, huh? So this is one other situation that you kind of need to just keep an eye out for. Occasionally you'll have this situation where you try to do integration by parts once, maybe you try to do it twice. Eventually you get back to seeing the exact same integral on the right side that you had on the left side. And then if you see that situation occurring, you can just treat that integral as a variable, add it to both sides, and then whatever constant you have, just divide by it at the end. Okay, any questions on that? All right, so I have two problems here. Well, actually, 4 different integrals to do. The first one, 3 parts to it. None of those are particularly difficult. But since this is the first time that you're seeing integration by parts, maybe a little bit tricky. That second problem is actually pretty tricky. So if you can figure that out, there is a hint on there that hopefully can help you. It's a hard problem. I'll say that. The first 3, hopefully we can at least try it. We can at least get a couple of those. So I'm going to give you guys a few minutes to work on these, maybe 5-10 minutes. I'm going to take a little break. I will be back. If you do have questions, let's see if Michael ever ended up joining us here. No, I guess he didn't. Oh, that's okay.
Yeah, I
If
made
you
it.
want to talk to each other, that's fine, or text or whatever, or chat. I mean. All right, so I'll be back in a few minutes. Go ahead and try to do the problem 1 and problem 2, and I'll come back and go through them. Okay, I'm back. So it looks like Michael was able to join us. Everybody
Barely.
see that stuff? How's it going, Michael? This is all your work, huh?
Oh yeah, they're kind of long.
Everybody see how that's done? This is helpful because I don't have to write it all down now. Um, did you guys get these answers for, let's see, what is the first one? Ln x squared. Looks like you had to do parts twice, huh?
Let's see. I don't even remember. I think so.
Yeah, it looks like integration by parts 2 times on that one. So it started out by making u be
Yeah, yeah, it is.
ln x squared. Everybody see how you have to remember the chain rule when you take that derivative the first time. If it's ln x squared, got to put that 2 down in front, lower the power, multiply by the derivative. That's where you get 2 ln x times 1 over x dx. So that's how you do that. So I think at this point, probably best if anybody does have any questions about these, go ahead and ask them. Otherwise, I'll let you guys look at this, copy it perhaps, download it, and then maybe screenshot it or something like that, and then work on it later, or just check to see that you got the right answer. I think that second problem, though, I kind of do want to go over because it's hard. It's a difficult problem. Let's just take a look at that one in particular. Yeah, see what he did on that second problem there? You had to say, you had to kind of split the function up so that you had x to the third times x squared times e to the x to the third. Yeah, what are you doing there?
Let's see.
Using t's instead, huh?
Which one are we looking at? You looking at?
I'm looking at problem 2.
Oh, okay. Problem 2. I see. Yeah, I broke up the. I wanted to make. I did basically a U sub from the start. So called. I used a T instead of a U, but so I could make the T the x cubed. So I was able to rewrite the integral.
Ah, I see.
So it still is the same integral because we got 3 over 3, the 1/3 out front and the 3 inside. And the x cubed and the x squared make the x to the fifth. So we still have the same integral.
Right. I see. Okay, yeah, so then you changed it, you basically did a substitution and changed it into a parts integral.
Right.
I see. Okay. So that's perfectly fine. That's a great way to do that, in fact. So everybody notice what he did there. I'm just going to show you an alternative way to do that. In fact, I think I gotta share my whiteboard again. Hold on one second.
For problem C, why is it that it is 1/3 x cubed times Lx instead of x squared times Lx for u dv?
Let's
So
see.
yeah, that so he's saying that v dv is x squared dx, right?
Yes. Yeah.
Yes. dv is, in fact, I think I can actually draw on this. Can I do that? Maybe not. Let's see. I'm gonna do a request for annotation. Yeah, so he said this, right? dv is x squared dx. So that means v is the antiderivative of that, right? Well, the antiderivative of x squared is 1/3 x cubed, right? Is that the question? Why is it 1/3 instead of 1/2?
Oh, yes. I see that now.
Yeah, that's just the power rule for integration. You got to remember that when you raise it to the number, then you also have to divide by that same number that you raised it to. Does that answer the question?
Yes.
Okay, cool. All right, let me go ahead and share the whiteboard because the way that Michael did that last one is, like I said, perfectly acceptable. Um, I'm just going to show you an alternative method for that third problem. Okay, so number two, alternative way, you have x to the, it's really kind of just it's the same thing he did, but it's just maybe a slightly different way of looking at it, I guess. What you can alternatively do is just rewrite this integral as x to the third times x squared e to the x to the third. And then you can just do parts right away from there. You can say that u is equal to x to the third, and dv is the rest of it, x squared e to the x to the third. Then that means to find v, well, let's see, let's just write du. Du is just going to be 3x squared dx. And then v, you have to integrate this thing to find v. Okay. Now, to do that particular integral, this integral, to find what v is, you have to do that by u sub. Okay, so I'm going to do a separate u sub here. I'm going to say that u is equal to x to the third, and then du is equal to 3x squared dx. And then I can divide both sides of that by 3 and get 1/3 du is equal to x squared dx. And so that integral is then going to become, this integral will then become, according to the integration by substitution, 1/3 of the integral of e to the u. And then du. So I'm just going to try to circle a few things so that we see exactly what's happening there. Here's the x squared dx, right? So look, there's the x squared dx. Try to circle that a little bit better. X squared dx, right? X squared and dx become 1/3 du. So there's the 1/3 and the du, right? And then the rest of it, what else do we have here? We've got the u is the x to the third, right? So boom, there it is. And that's the u right there. Okay? And so that integral then becomes 1/3 e to the u, which is the same as 1/3 e to the power of x to the third. Okay, and now all of that was done just to figure out what v is, right? And so that means coming back up to the top, this whole thing that we started with can then be written as uv, so x to the third, and then we'll just put the 1/3 in front, e to the x to the third. So that's the u and the v minus the integral v du. What was du? I guess I'll just write all of it. V du. What was v? 1/3 e to the x to the third, so 1/3 e to the x to the third. Du was 3x squared dx. So this is u, right? U v du, right? So v is 130. Yeah, this is the v, and this is the du. And remember that v, that's the same v that we just got up here with that u sub. Okay, simplifying this, we're going to get 1/3 x to the third, e to the x to the third. The 3 and the 1/3 cancel, so we're going to get minus the integral e to the x to the third. Or actually, let's write it as x squared e to the x to the third. Okay, now if you look at the integral that we ended up with, that is in fact the same integral that we already did up here, right? That's the same integral that we did right there to find what v was, right? And so we already have, we don't have to do that work again. We can just say what that is because we've already done the work for that. This is 1/3 x to the third e to the x to the third minus, what did we just get for that other one? 1/3 e to the x to the third. I hope that's the same answer that you got there, Michael. Is that right?
Let's see. 1/3 x, so that factors out and we leave x cubed minus 1. Yeah.
Okay, perfect. All right, so there's, again, two different ways to kind of look at this one. The way that Michael did it was he did the substitution first, and then that became a new integral that could be done by parts. The way I approached it was I just did it by parts immediately. I split the integral up so that we could do it by parts, and then in order to find the v of the parts formula, we had to do a substitution to make that happen. So anyway, two different sort of methods of looking at this.